Welcome. Today, we're diving into the sources of experimental error. Understanding where errors come from is key to improving our experiments and getting reliable results. We'll explore common pitfalls, how they affect outcomes, and what we can do to minimize them. Let's get started. Let's start with an introduction. This is where we set the stage, outline what we're exploring together. It's the moment to get a clear sense of the topic, why it matters, and what we're aiming to uncover. Think of it as the roadmap for our journey ahead, helping us stay focused and connected as we dive deeper. When we talk about experimental errors, they fall into three main categories. First, systematic errors. These are consistent mistakes that push results in the same direction every time. Think calibration issues or instrument bias. Next, random errors. These are unpredictable, caused by things like temperature changes or slight differences in how an analyst works. Finally, gross errors. These are human blunders, like mixing up samples or making calculation mistakes, which can completely invalidate results. Understanding these helps us improve accuracy. Systematic errors often come from the instruments we rely on. These can stem from things like improper calibration, instrument drift over time, detector malfunctions, or worn components. For example, if an HPLC detector isn't calibrated correctly, it might consistently report assay results that are 2% higher than they should be. To keep these errors in check, we use regular calibration programs, preventive maintenance, and system suitability testing, all designed to catch problems before they affect our data. When we talk about errors in analytical methods, there are a few common causes we need to watch out for. Things like incomplete extraction, poor sample preparation, or using the wrong analytical conditions can all lead us astray. Sometimes, the method itself just has limitations. For example, if a sample doesn't fully dissolve, we might underestimate the active ingredient's potency. Regulators expect us to use validated methods, following guidelines from groups like the International Council for Harmonization and the United States Pharmacopoeia. That's how we keep our results reliable. When it comes to personal or human errors in the lab, a lot of them come down to simple mistakes by the analyst. Things like incorrect pipetting, improper weighing, misreading values, or calculation errors. For example, if the actual weight is 100 milligrams but the recorded weight is 110, that's a 10% positive bias, a significant error. To prevent this, we rely on thorough training programs, strict adherence to standard operating procedures, and independent verification to catch mistakes before they cause problems. Let's talk about the environmental factors that can influence our laboratory work. Things like temperature, humidity, vibration, airflow, and lighting all play a role. For example, even small temperature changes can affect the sensitivity of an analytical balance, causing weighing errors. That's why good manufacturing practice requires us to maintain a controlled environment. Typically, this means keeping the temperature between 20 and 25 degrees Celsius, with relative humidity around 40 to 60%. These conditions help ensure accuracy and consistency in our results. Sampling errors are among the biggest culprits when it comes to mistakes in testing. They happen when the sample we take doesn't truly represent the whole batch. This can be due to poor mixing, materials separating out, or simply using the wrong technique to collect the sample. For example, if a powder blend has zones with too much or too little active ingredient, a bad sample might give us a false reading. That's why good manufacturing practice demands sampling plans that are backed by solid science. Now, let's talk about how we calculate absolute error. This measure tells us the size of the difference between a predicted value and the actual value, without worrying about direction. It's simply the absolute value of their difference. Absolute error helps us understand how far off we are, in clear, straightforward terms. It's a fundamental step in evaluating accuracy, giving us a direct sense of the magnitude of any mistakes we make. When we talk about precision, we're really focusing on consistency, how close repeated measurements are to each other. Random error, on the other hand, is the unpredictable variation that creeps in every time we measure. It's the noise in the system, the little fluctuations that keep us from getting the exact same result twice. Understanding both helps us improve our methods and trust our data more. Let's look at the tools we use to get to the bottom of problems. We have the fishbone diagram, 5Y analysis, and FMEA, all designed to dig deep. When we spot an error, like an out-of-spec result, an out-of-trend pattern, or something unusual, we review key areas. That means the analyst, the instrument, the method, the material, and the environment. Our objective is clear: to determine the assignable root cause. That's how we turn errors into learning. When it comes to preventing errors, we focus on a quality risk-based approach. That means identifying where things can go wrong and putting controls in place to stop them. In the lab, this includes calibration programs, equipment qualification, method validation, and thorough analyst training. We also monitor the environment, enforce strict SOP compliance, and have robust data review procedures. Beyond processes, we foster a quality culture that encourages getting it right the first time, every time. This mindset is just as important as any checklist. We've looked closely at how experimental errors influence the quality of our data and the decisions we make. These errors come in different forms: systematic, random, or gross, and arise from instruments, methods, analysts, the environment, or sampling. Using statistical tools like percent error and relative standard deviation helps us measure performance clearly. Regulatory bodies expect us to investigate these errors thoroughly and apply corrective actions. Strong lab controls are key to minimizing variability and staying compliant. Managing errors well isn't just good practice, it's essential for quality and safety. Thanks for joining me today. If you want to dive deeper or have any questions, don't hesitate to reach out. I appreciate your time and attention, and I look forward to continuing the conversation. Thank you.